said in terms of reference yesterday, I was starting to be a little on lists, and then I realized that they were all into these partial selection of reviews that have been published in the recent years. But if you go through these reviews, they have impressive set of references in them, and in addition to the two textbooks that are useful. So, where did I stop? I stopped right about there, right? Tell me my comment.
What?
All right. So I'm back into that will do if we keep this pointing. It's pretty hard. So do you remember the game we're playing first is called induction. That is, you apply a magnetic field and try to see what a flow is doing to that magnetic field. So in that particular case, it's what I was showing yesterday with the with my scarf. Is you apply a magnetic field like this, and then you apply differential rotation, and that creates that. So you have one way to see it is the torsion of the magnetic field lines. Okay. One way to see it, which is, do I need this?
No, I have perhaps.
I thought I was being loud enough. Another way to see it, which of course is not useful in that case, but is useful when you're trying to think about it, is with the induced currents. I don't know how you guys learn electromagnetism, but in France you use this finger rule. And trying to decide, of course, you gotta use the right hand.
The bottle of whiskey is better, but it won't work in France.
No, we use quartz. It goes like this.
Yeah, this would do.
I've had entire exams in my lab where I was looking at my left hand and got all the signs wrong. So if you do this though, and if you have the flow going in one direction here like this, and you have a magnetic field that is here, you'll see immediately that it will induce a current in that direction here, and if it rotates in the opposite direction, it induces a current in the opposite direction here. And all you have to do is close that loop, and if you have a loop, then you create that toroidal field, that you want. It's not foolproof, but it sometimes is an easy way to think about it. Now, if you go back to the...
Sorry, Jean-François, isn't it called Gauss dynamo? These two vortices rotating in opposite directions.
Yeah?
No.
The only, the one dynamo that I know that works exactly like this is the Lawson-Wilkinson dynamo, of course. Huh? Hudsenberg. I mean, Hudsenberg is the one that made those calculations with a finite cylinder inside a matrix, right? But you can drive. So these immediately. So I was going to say two things. One is how you get the induced field is by looking at the induction equation and saying that V grad U minus delta B. And what usually does with liquid metals where things are slow and the magnetic field is a slow beast, you say, well, that almost doesn't change, so you balance this with that. And that what says that the azimuthal field here is due to the variation of the azimuthal velocity with the direction of the applied field. And the number in between is the magnetic Reynolds number. Actually, when comparing different experiments, it's very useful experimentally to define the magnetic Reynolds number like this. That is, instead of using UL over lambda and trying to guess what is the right L, what is the right U, what is, okay? What you do is you just use linear response theory and you say that coefficient that says how much magnetic field is induction by nu is a definition of the magnetic Reynolds number. And that's very useful when you compare different sets of experiments that have different sets of geometries. The other is, of course, this effect is the Hertz-Berg dynamo. So if you have a cylinder like this, and the magnetic field going this direction, and you rotate this direction, okay, the twisting is going to create some magnetic fields in a direction like this, and here you put another cylinder rotating in that direction, then the twisting of that magnetic field line is going to make a field which turns out to be in the original direction again. And that's the fantastic experiment by Lowe's and Wilkinson in Newcastle.
Make sure it's not 90 degrees. 90 degrees wouldn't work, but
excuse me?
90 degrees wouldn't work, but other angles would work.
Yes, exactly. 90 degrees will not work. There's many things about the dynamo that it's a fantastic example to study both from the theoretical point of view and also from the experimental point of view. It turns out that it works experimentally only because there's a piece of tape here that prevents the currents from looping back right where they started, and then they'll have to do this in order to produce the toroidal thing. If you don't put the little piece of tape, then the threshold is higher. It again has to do how you bring the threshold into what you can do, right? So I don't think it's crucial for the dynamo, but that's what you learn from PhD thesis and stuff are always a lot more interesting than articles because they tell you the little stories, which you don't learn in articles. Okay, so with the so it's a first order effect. The toroidal field is linear with the applied field. So with the method I described before, it gives a little better picture than the one I tried to give you before, either twisting or that induction thing. You can really compute what is the electromotive force, what is the current, and you see that it is induction here, it is potential difference here, and the path the currents actually follow is not exactly the one that you draw with your hand if you plot current lines in the simulation. So you basically understand how it works, and you do the measurements. So what you do is you start the flow, have a differential rotation, put a probe where the star is, and you should see that if you measure the toroidal component of the field, you should see that it increases linearly as a function of the magnetic Reynolds number. Okay? With a very good factor, right? You can get as much toroidal field as you apply, because this is induced divided by apply of the order of 1. So that's how it starts, and that works out fine, and then it saturates. It saturates because after a value you cannot get any more field in that, and the process of saturation here is just what Anwar described yesterday, which is field expulsion. Yes?
Even in nonlinear saturation states, still you can calculate Rm using this. That's why u theta becomes now, when d by dz of u theta can become function of b.
No,
still you can calculate
no. In these experiments, in what I'll describe when I do inductions in liquid metals, u is fixed. The interaction parameter is the order of 10 to the minus 5. Okay, so the flow is, in these experiments here, the magnetic field is not hitting on the flow. All right, there's no change in the flow. The Rn that we compute here is the one given by the slope. And the saturation here is the mechanism you described yesterday. You try to push a field through those loops here, those toroidal loops of flow, and they'll be expelled. They'll tend to go away, and that's why you saturate. Now, that's the picture you shown yesterday, and that's or one like it, which is taken from Keith Moffat's book. And this is the distortion of magnetic field lines. When you increase the magnetic Reynolds number, leading to eventually to the expulsion, as you saw in the film. Well, you can measure this. You apply a field like this, you put a probe inside the flow, and you do measurements at different depths, and you see that if you started from originally horizontal straight line, you increase the angle as you go down. Of course, the magnetic Reynolds number in those, in that case, liquid gallium experiments is of the order of 1. Okay, so you don't expel completely the thing, but you have a fairly good agreement between the profile of magnetic field with radius, which you measure, and what can be computed using any of the formulas given by Keith Moffat, Nigel Weiss, Michael Proctor. It turns out to be these profile here. And that's the sequence that I don't need to show you, showed it yesterday. So that expulsion here of the magnetic field is what is causing the saturation here. And we'll also see the saturation in other measurements. Okay, so the next effect you want, so still doing the exercises here, you want to see differential rotation, all right, we'll have that. You want to see the expulsion because it's something that happens everywhere. So we've measured that, so we go through the exercises and there is nothing to be seen here. Okay, so what we're looking at here is the alpha effect in the sense of Parker's mechanism. What you have is you have a twist of a twisting flow, then you do a loop like this, and you turn it, and you turn the flow. You have magnetic fields, you create a current. This is opposed to the original magnetic field. Too bad the picture was pretty good on this one. Alright, so if you start from a straight magnetic field line, and you have that flow created in the cylinder by the rotation of one disk alone, then you have a colloidal flow, which is just like that. And then, of course, you induce rotation because it rotates and you have that swirling flow. And the numerical simulation, when you do on this, say if you take an originally magnetic field line like this, you'll twist it, and then if you do that, you produce a component of current which is parallel to the magnetic field you apply. So this was the simulation. It's a little bit harder to understand when you try to play with your hands with a cork. I don't know how you want to do it, but if you try with one component so you apply a magnetic field which is transverse, right? It's moving like this, the magnetic field is transverse. Okay, first you do it with a downward motion. The downward motion is going to create a current which is parallel to B cross B. This is the yellow line here, and that sheet of current produces this induced field, which if I do it like this, it will be like this in the opposite direction. And now if you apply the toroidal velocity on this, that will create an induced current which was anti-parallel with the one you started with. Again, it's not, there's hundreds of ways to understand all this, right? But it turns out to be nice when you can look at it from different perspectives and agree that what you see is what you should.
No problem. In your experiment,
yes,
is the velocity that's going round and round on the propeller not similar to the velocity that's coming in?
Yeah, it's the ratio of, so the question is colloidal to toroidal ratio, right?
Yeah.
So the ratio of colloidal to toroidal ratio is set by the size of the little blades we put on the disc.
Yeah.
And in short of knowing anything better, which you need so that it is 1. And that's after the papers by Dudley and James that says that you get the better effect when both of them are 1. So now, if you look at it again from the sketch of the distortion of the field line, now that's using the induction equation, another way to look at it, from the uniform field B naught. Then you have the first induced field, which depends on how the field varies in the azimuthal direction, and the second one depends on how the vertical field varies transverse to the applied field. The result is that in the end you have an Rm squared effect. Okay? And now when you do the measurements, what you see again is that, in order to do the measurements, what you do is you apply, oh, I have it here. You apply a magnetic field transverse to the swirling motion, and then if that creates a component of current which is opposed to it like this, that generates an induced magnetic field which is vertical in my drawing. Okay? Now, you measure the component, you measure the amplitude of that vertical axial field when you increase the magnetic Reynolds number, and what you see is first a quadratic effect, and of course in the end the expulsion, because the whole thing rotates. Okay? And that expulsion can be thought of alpha quenching in some models. Now, here is one effect that took us almost 3 years to understand. And it comes directly from what I said, is in a cylinder like this, when you have induced currents, they cannot go out. Okay? Because ultimately, even if here you have, so think of it as being sodium or gallium, think of this as being stainless steel or copper, but outside is a non-conducting medium, right? So if currents are generated by the fluid motions, they have to loop back within that volume. And the fact that they loop back and don't go to infinity produces additional effects, okay, that are due to just how much electrical jump you have across the interface. Now in that case, one way to look at it is to look at the induction equation by adding one term of the non-homogeneity in conductivity. Here mu is equal to mu naught. And this new term here leads to a new effect. Let me give you the picture of what happens before we do the math. Oh, shoot. Oh. All right. So I'll have to do, there's nothing to be seen, right?
No.
A little bit. What do you mean?
A little bit. Okay. Now,
Well,
suppose...
maybe reduce the light.
Yes.
Maybe take the laser pointer so can point precisely.
Suppose you apply a magnetic field transverse to the cylinder where you have differential rotation like this. Okay? Now, that differential rotation here is creating an induced component which is in opposite direction on each side, right? Now, having a field like this has to be associated with a current pattern that goes like this. Okay? A magnetic field, that's if you want, that's the Herzenberg dipole because of applying a field perpendicular to a rotating piece of conductor. That's the one here. Now if you have a field which has been generated in that direction here, in this direction here, you need these current sheets, okay, which loop inside. Alright? But now the circulation of these currents here, exactly at this point, creates a magnetic field. Okay? If you want to see it a little more easily, but it's not entirely correct to say that this induced field has to loop back. And that's what it does. Okay? But I have no conservation law of the magnetic field having to loop back inside. Whereas the currents, I know they have to do exactly this. Okay? Now, that effect here is totally due to the boundary conditions. You change the outer vessel from stainless steel to copper to something else, then you'll change the magnitude of this effect. Right? The source of what you see here is the magnetic field that has been produced at the top and bottom, and that exists in the entire flow because the currents that were produced at the top and bottom have to loop back inside the volume. It's a trivial effect, but it tells you that in these kind of experiments, the currents have the distribution having to loop back inside the volume, and what you have to, when you measure something, it might not be generated locally. Okay, it might be an effect of things being in a finite volume. It's not periodic in all directions, those experiments. All right, so that's the end of part one, which was just going through the exercise of Paul Roberts or Keith Moffat's book, right? You end up with the fact that helicity is important and generates nonlinear effects. Differential equation converts colloidal to toroidal. Helicity can, in principle, do the reverse, and you'll, of course, you're going to find field expulsion. All right. Now, a little comment on small scales, and part of this might not be agreeable to everyone. That's my vision of it. So what I've described so far has been the flow into a box like this. If you look at pictures of that in a water experiment, that's the kind of thing you see. So if you do long time exposures, by long time meaning you leave the camera open for one rotation, okay? In which case you see patterns like this, where those rolls here are due to the fact that you have the differential rotation in the mid-plane, and that differential rotation in the mid-plane is an unstable shear and might produce Kelvin-Helmholtz type of vortices. All right, that's the type of stuff that you see here.
So where are the propellers? On the top?
Oh, there's top and bottom. Top and bottom rotating in opposite direction. So in the mid layer you have this here. Okay? And now, if you take an instantaneous picture of what you see, of the flow, that's what you see. That's the one on the right, which has nothing to do with this. Okay? And then you start thinking, all right, we're building dynamo cycles based on mean flow, but that mean flow never happens, right? And so what's the result of this? It's just like, well, this is wrong in the end, but my thinking of it at the time was that suppose that you're throwing a coin, okay, with +1 and -1, and you find out that the average, which is 0, is a dynamo. Okay, you never get 0. Right? Okay, it's one of those fluctuating things.
So why it is not axis symmetric? So that there is what? This vortex, this left picture. So what exactly happens here?
Because if you leave it open for an infinite time, that's what you see. Okay. Now, if you look at it of the order of 1 revolution, that's what you see. It means that you have an instability. That instability has broken that symmetry and is made that structure, so that radial vortex. And now, in any case like this, what happens is in the course of time that radial vortex rotates slowly, right? So that on average it disappears, okay? And you still have that nice uncommon structure, all right? But it says your problem has a whole bunch of different scales, and the one that I've been describing so far is this one plus a little bit of that one. I didn't go into details, but there's some effect of that for understanding the large scales. All right? Now what I'll discuss now is the effect of this, the mess, the small scale fluctuations. So when I was plotting magnetic fields for the past minutes or so, what I was plotting is the value on the red line. Okay, so I was looking at how that mean value changes with control parameters. Now the signal you get from a whole probe in the flow is this one here. Okay, so you can see immediately that there's a lot more to it than just the mean value. The histogram is so wide, and it has some self-similar structure in a sense. So it really is a turbulence problem. That's another point of the large scales. This effect, oops, where is it? This effect here, okay? What I'll show you is here. What I've done is insert into the flow a probe that has a number of sensors, okay, in order to record a profile. All right, and then I'm playing that. So I'm playing that profile as a function of time. Each of these blue points is the mean value which I was showing on the previous picture. But if I take a low-pass filter, those mean values will evolve slowly in the order of the frequency of rotation. Gives you an idea what the stability of those induction effects that you have, and that's what it looks like. You see, the concept of a mean makes you think a little bit. But at least in that case, it has that rounded shape, right? So you could think of it as being a little more intense, a little less intense, fluctuates, but it has the rounded shape. Look what's happening on the right.
What is CL?
Huh?
C.L.
Boundary condition effect. It's just slightly different geometry. So in one case I was looking at the direction of rotation directly, the other case I was looking a little more into induction effect that are linked to the instability in the shell layer. If you look at this one again, you see that not only does it change the profile, but it almost never has that average shape. Okay? So what I'm saying with this is one has to be careful with the fluctuations. What you think as building blocks of dynamo loop-back mechanism, like the beautiful one you've drawn, all right, in reality, because of the turbulence, has large-scale fluctuations of tremendous importance and small-scale fluctuations. All right, now we should worry about it. So, this is conventional measurements for turbulence. Kolmogorov turbulence inside the flow. So what you see here is a recording of a magnetic, of a pressure probe at the flow wall. Okay, so this is in time what pressure you see on a probe at the wall, and this minus 7/3 spectrum is characteristic of fully developed Kolmogorov-like turbulence, as we see in a minute. So the proper framework for this developed thing is Kolmogorov theory, right? K41 plus small corrections. So what you think about when in a situation where you're not changing the flow too much is that red is velocity, so you have a velocity cascade down to a small scale, okay, which is given by diffusion, and then you have another cascade of magnetic energy flowing to the small scales to another scale, and the ratio of these two scales is the magnetic Prandtl number to the 3/4. Yes. Yes. Mm-hmm. No, it's the magnetic. Yeah, this is Reynolds to the 3/4. So this is magnetic Prandtl number to the 3/4. In the situation where the magnetic diffusivity is way larger than the hydrodynamic one, you do have a fair amount of scale separation in between those two things. However, you have very little scale separation between where you inject magnetic energy and where you dissipate it. So it's not unreasonable to assume, and we'll come back to it, to the mean, all sorts of mean field theories, to assume that if you have the whole range of scales that are acting on the magnetic field, you could somehow model or subgrid model what's happening here. So what is expected from the induction equation like this? If you say, again, this is a quasi-static approximation and slow, then this is in equilibrium with this, meaning that the magnetic scaling B of k squared is k minus 2u squared k, which you mean that these will have to decrease like minus 11/3. that's indeed what you see. The pressure goes like, I mean, P is rho U squared. U in the Kolmogorov theory, delta U goes like the separation to the 1/3, the square to the 2/3. So P squared goes like the separation to the 4/3. So the spectrum is minus 4/3 minus 1. I don't know why I needed to copy it. So minus 4/3 minus 1 just turns out to be minus 7/3. And the minus
equality, right?
Yeah, that's what I wanted to do, I think. And the minus 7/3 is the one I was showing you on pressure. And if you do a simultaneous measurement of pressure and magnetic field, one goes like minus 7/3 and one goes like minus 11/3, where the red line here is conveniently placed above the data so that you could believe that this is a straight line. You don't have to.
There is an imposed field, right? You had an imposed.
In every case, it's an imposed field. So I haven't gone into dynamo at all. Okay. Well, it's not worse a straight line than any numerical simulation.
Excellent. Why?
Huh?
Of course, it's excellent.
Bon. All right. So the picture we have when you impose a magnetic field for the spectrum of magnetic fluctuations is the following one. At the low end, you have minus 11/3 type of Kolmogorov behavior. Of course, if you go to extremely long time, theory says that fluctuations become uncorrelated. Therefore, the spectrum has to be flat. And in between, there's a region with a different exponent.
Do you know why?
Huh?
Do you know why?
No, that's the one I don't know why, and that's the one. You know why? You know why it's minus 1?
Yes.
Wow. All right. So it's a shame that Kerry Forrest is not here because he strongly believes that this is minus 5/3. So I put minus 1 because I like minus 1 for various reasons. But okay. So what's your explanation?
It's the same. If you take the same arguments to get the Golitsyn spectrum minus 11/3, but assume that magnetic field is homogeneous, so tangling of homogeneous field by Kolmogorov turbulence gives you minus 1.
At large scales.
Yes. And then further down, it becomes 11/3.
All right. I need to discuss this with you in more detail.
Yep.
But I understand your full.
Shukurov 82, right?
82, yes.
Yeah. So one more
You see,
reference
actually.
should be see.
Minus 1.
There's plenty of it. This minus 1 is yes. All right. So.
But this is 1 over F noise you're saying, right? No?
The problem I have with this is that if you measure some hydrodynamic quantities in the absence of applied magnetic field, you also have slow evolution with the minus 1 thing in hydrodynamics.
But here you have applied field, right?
But here I have an applied field. Granted. All right. So because of the amount of theory we need, what I'll describe now is a bunch of work that we've done with our colleagues in Perm, Russia. So it's all the group around Peter Frick, Rodion Stepanov, and the others. And we try to go after measuring some small-scale mean field quantities. And to give you the result bluntly, at least at the low magnetic Prandtl number that we do the measurements, we failed miserably. My views here are a little bit biased by these experimental findings. Not total failure, I'll show you, but not what we expected in the beginning. So I guess Karl Heinz has been going through the mean field and all. This is just the most simple version you can read in Moffat's book. The reason why I put these up here, at least in the most simple case, and I think I will convince you that the most simple case is not so well adapted for real experiments. You need to go beyond that, as Karl Heinz and Rodion Stepanov did. And I'll show the results of that. But in the most simple case, you first start from the velocity correlation function. Everything stems from that correlator, which is up there. Then you play all kind of magic on it, but you only had that to start with. And it's always been a problem for me to understand really how, given the dynamics of that, I could end up with two very different dynamics for the energy and for the helicity, leading to coefficients that would be different. In one case, not change so much. In the other case, change very much. And the whole concept, I have to say straight off the bat, that the whole concept of a helicity cascade in the experiments is something that is completely eluding me. It's something that I have never seen any evidence of persistence of helicity when you try to inject it into a flow.
Kinetic.
But we have a low Reynolds number, magnetic Reynolds number.
I have a low magnetic Reynolds number. What has been shown in recent, and that again has been shown in recent simulation by Pablo Minini and Annick Bouquet, is that the return to isotropy is going to be very fast on the helicity, actually of the same order of magnitude if you take an ABC flow or a telegreen flow, meaning that helicity will tend rapidly to go back to isotropy with helicity of all signs in all directions and probably not even surviving. Whereas that persistence of helicity is what I was mentioning yesterday, changes dramatically if you add rotation. Okay? So either in the experiments where people have done grid generated turbulence or helicity injected with little propellers, and then you start a rotating flow, then you see a strong persistence of that. Whereas, meaning that the concept of helicity cascade is strongly enhanced by the rotation. In the case of a flow where there is no global rotation on it, it seems to be, at least to me, not so obvious at moderate Rm that it survives so well. So the concept of mean field, I'm just putting these slides up to show you that in mean field theory you need a guide. You see, and so we only work our way through this because Rodan Stepanov was kind enough to explain to us what he's been doing with collides. Because if you throw this in my face just like that, you need a guide to be able to read this. But what I want to stress is it has some experimental relevance, lots of it, but you need a guide to read this. So the experimental relevance is the following one. The perm screw flow is the ultimate helicity generator that I know in the lab, alongside with the Riga experiment, right? So what they do is imagine a wheel, okay, a torus. You set that torus into motion. Here is the torus. Okay, you spin it at constant, increase the speed, so it's solid body rotation. Okay, everything moves together, and at time t equal t naught, stop it. Okay, we're talking about a torus that has maybe 50 centimeters in diameter, that holds a few dozen liters a gallon. Okay, and you stop all this in 0.1 seconds. Actually, a little bit under this, 0.0304. And when it stops, you have the fluid going through a propeller-shaped diverter here and here. And the fluid is starting to swirl in motion like this because the vessel stops, the fluid pushes forward and starts that spinning motion. So it's a Riga in torus geometry, periodic boundary conditions, all right, in a way. And once you do that, you create those, it's too bad you can't see.
No, you can see it.
You create those helical wave motion here that you can see and decay. So this is the ultimate helicity generator, all right? And when you do induction on this, you apply magnetic field which may be either transverse to the torus, so if a helical motion goes like this, you will see it coming through, or you have a current going through the center of the torus in which case you apply a field along the axis of the torus, in which case the helices that pass like this will give a cross-section of B cross helicity, and you look at what you see. All right? And after almost 6 months of very careful measurements, the results are the following one. In the transverse direction, so you stop, that's the decay of the induced magnetic field, which decays like the motion. Okay? And you look for, the first thing you ask is, what kind of contribution has exactly the right symmetries with helicity? Because you can do 4 things in a setup like this. You can rotate in one direction, rotate in the other direction, have left-handed propellers or right-handed propellers. Okay? When you compare all this, you change the helicity in your system. And the thing that has to be linked with helicity has to have the same symmetries. So you go through the whole thing, and you see that there is only one candidate that survived immediately at the time where you stop the flow. All right? And in the alpha tensor, and that's where the work of Karl-Heinz and Roden-Stepanov came in, there's only one candidate that is able of producing this with the right symmetry and exactly the right order of magnitude, is the turbulence wave, which is, the flow is in solid body rotation. You stop it, it starts pushing forward. So immediately behind the diverter, it is fully turbulent, or at least turbulent, and before it's solid body rotation. And that wave is propagating into the fluid until it does one round. And the propagation of that wave across the torus is what sets that induction peak here, which is related to the gradient of, I think it's called G, U squared average. It has the right amount of the right magnitude and the right symmetries, but it's the only one that survives. And when you do this, you find that for all your efforts of stopping a flow with velocities of the order of 20 meters per second and setting full helicity, that buys you an alpha of the order of a millimeter per second. Small. Nothing comparable to what you would derive using standard homogeneous isotropy thing. It is small. Okay? Again, it may be a low RM, low PM effect, but that's what comes out of the experiment. So, it's this term here, and it's just what I said. It buys you an order of 10 to the minus 3 result. So, there is an effect, and if you trust that effect and you try to scale gallium to sodium, so how much of the alpha effect you would expect in a sodium experiment like the one in Cadarache and all this is alpha equal to 10 centimeters per second. Okay? I want you to remember that order of magnitude, because when we go back to Cadarache generation of dynamo, we'll have to think about it. What am I? Okay. So alpha turned out to be much smaller than what you would have expected before we started all this. How about beta? Beta is a very hard measurement. I won't have time to discuss it, but I'm willing to mention it aloud. There's a paper by Brown and somebody else in PRL in 2003 that claims to have measured a beta effect of the order of 10%. I'm willing to discuss with anyone that paper is just wrong. Everything is done wrong. So the only measurements, direct measurements of beta that I know of is by the group of Perm. The previous measurements of alpha is a collaboration between our group and Peter Frick's group, and this is something that they've done separately. So the way to measure this is beta being a diffusivity. Experimentally, you want to see it as a penetration depth. Okay, how far the field goes into the fluid. So what you do is you apply an AC current in a coil, which is wound across the loop, and that creates. You look at how the induction all right, results from it. So first, for a given field with the coil wound around the torus, you compute the field that you get inside, all right? And here the geometry is important because you have to be able to compute these quantities. Then, from the fact that flux is in the induction times the current, you compute the induction. And once you have that, you go back to the relationship between current and voltage, and you derive what is the change in phase shift between voltage and current as a function of applied currents and other parameters. All right? You need to be able to do this. Once you've done that, the first thing you do is you check that when you change the temperature of the system, you get the right electrical conductivity. Okay? The effect that is measured in the end is of the order of a few percent. So at the order of a few percent, temperature matters. Okay? So the first thing you do is you take the handbook, all right? See what they've measured for gallium at different temperatures. Don't find many things, so hunt for references. And of course, the Russians done it. and so you need to find a published reference, carefully measure all this, and you find that the points here are what is being measured at two different frequencies. With two different kind of gallium, and that's how much of a phase shift you get with the temperature. And if you look at it, that's exactly what you expect from tabulated values. All right? So once you've done that homework, and this is not an easy homework, there's any kind of impurity and all these changes all these things. Once you've done that, you go to the flow, and you look at how, on average, does the angle between voltage and current shift when you stop the flow, and that as a function of time. You have strong velocity, and that's this change here. And when you look at this change and you translate using the formulas I was showing you before back into all the parameters, okay, this is how much of a change in conductivity with respect to molecular conductivity you get once you do that. So it's in percentage, it's between 1 and 2%. And I guess this is very consistent with the observation in Riga that the threshold, or in Karlsruhe for that matter, that the threshold is basically where you compute it without accounting for an effective turbulent diffusivity. Am I correct, Grace? I think, how much was it? 2% maximum if you put an upper value in the change in the critical value of Rm compared to simulations that don't account for turbulence.
1%.
1%.
0.1.
0.1%.
0.1.
Okay. So this is small. Okay. The beta effect either measured here where Rm in these experiments is of the order of 1 to 5. In the sodium experiments in Riga and Karlsruhe, it's the order of 30 to 50. So at these order of magnitudes, the beta values are in the order of percent. So the point is, if you want to use any scaling laws like beta is, can't remember it, u squared times tau, no, divided by tau, times tau. No, huh? 1/3 of u squared times tau, and if you try to guess tau and you try to guess u squared, and you even take 1/3 of this, it turns out to be wrong in that case. Okay? I'm not saying it should be right. I'm saying that that's not the correct estimate.
But from this low, for low Rm, I think beta will also be proportional to lambda, the conductivity, right? It will be also small, or not?
Beta is proportional to Rm for small Rm. Is that what you mean?
Yeah.
Of course it's small then.
Like alpha also.
Yeah.
The soccer calculations give you alpha and beta proportional to Rm.
Yes.
I just want to say that in those fully turbulent things, those contributions from small scales are small. There's another fact that I don't know what to do with, but I'm showing you anyway, is something that we should look more into, but we haven't, because ever since we found the dynamo, we've had better things to do. But here is one thing I'd like to understand so we take the washing machine, and on one side of the walls we put a small, very strong magnet. Okay, so there's a permanent magnet there, and you measure what is the fluctuation of the magnetic field inside. All right, and what is being found is you have very efficient transport of that magnetic field throughout the volume. All right, if there is a source of magnetic field somewhere, the flow will transport it very efficiently. Okay, and with fluctuations that are extremely non-Gaussian. I don't know if that is important in real life or no, whether we should study this more, but the fact that field generated from some place can be carried out with what efficiency and into what quantities from here to there, I think has some relevance in maybe, but we haven't studied this in detail.
But this will also give you the estimate of the turbulent diffusivity, right?
Thank you, Edward. So we're coming to another point I wanted to make, and this one is a physical one. Is alpha, beta, and all the others, as we discussed yesterday, but I'll make it aloud, are transport coefficients. So what they do is they answer to the question what flux goes in what direction, given the fact that you apply this gradient, or the transport coefficient. Now, in kinetic gas theories, you only need one process, the collisions, to give you most of the transport coefficients. So they have, the Prandtl numbers are 1, basically. So it's the same origin for all these transport coefficients, and you get a value of viscosity, for instance, okay, which is the same as if the mechanism is the same as the Prandtl number, we guess, so of the order of 1. Okay. Now, when you take a turbulent fluid like this, the transport coefficient may depend on what questions you're asking. It doesn't say that the viscosity that says how momentum or angular momentum is being transported is the same viscosity that says how things get dissipated, which is the same viscosity as this. You know what I mean? You're doing a modeling, and the modeling you do may depend on the question you ask. All right? For instance, for the dissipation, people tend to think that the currents happen in current sheets. All right? And that might have some relevance, which might not be relevant for the transport of angular momentum. Okay? So computing in a turbulent flow 1 alpha or 1 beta depends really answering a particular, a well-defined question. Like, for instance, if CD is the alpha of the electromotive effect, what you should be doing is find a way to measure the electromotive force. Okay, the gradients of B and divide. Now, if you want the diffusion, if that one is related to diffusion, you have to model how J squared over sigma integrated over the volume varies. And if that varies like a coefficient times the gradient B squared, that might be the beta you want. One question which may not be exactly, I want to stress this, even the equations, once you, it depends at which step you want to do the modeling. In those non-linear stuff, it is not obvious at all, and there's many counterexamples that if you do the modeling at one step and then do the averaging of the rest of the approximation, is the same as doing the averaging and the rest and doing the modeling in the end. That is, the order in which you do things matter. That's, I guess, is what I'm trying to say. So it might not be just one value of these things. All right. These concerns, that point is settled now, but in some form. But I'd like to stress it though. In these concerns, the fact that there's possibility effect of turbulence being a diffusive mechanism, plus the fact that you've seen the profiles fluctuating before, meaning the mean induced processes, all right, might be fluctuating a lot, has run to something that back 5-6 years ago was called the runaway problem. It's something that, who was that? Alexander Shekoshin and colleagues stumbled upon is that when they did numerical simulation of dynamo action, they found that once you the threshold keeps increasing. All right, you increase the turbulence, and the threshold for dynamo action increase. All right. Now, if you think about in the simple terms, and at that time the questions were not resolved, you think about the simple terms of alpha and beta from homogeneous isotropic turbulence theory. You increase alpha, but you increase beta, but just the same amount, and the ratio of the two is not buying you anything. So you get a more and more complex flow, and the threshold is just running away. And that has been confirmed by a group of François Daviau, Bérangère de Brul in Saclay, where you take an ordinary flow and you artificially add fluctuations. So you take I think what they had in that time is a Taylor Green flow. So you put flow equal Taylor Green flow plus fluctuation, which you put by hand. Okay, you throw this into a kinematic simulation, and you see that no matter how you add the fluctuations here, delta and delta 2 are just two different definitions. The threshold goes up. Okay, when you add fluctuations. All right, and this is a worrying business. the gallium sodium flows are incredibly high level of fluctuations. You see, the threshold might be running away in the same manner. So, with the help of Yannick Ponty, Pablo Minini, and Annick Pouquet, they've taken up the simulation of Taylor Green flows in kinematic dynamo simulation, and look at how the critical magnetic Reynolds number is increasing when you're decreasing the Prandtl number, which is when you're increasing Reynolds. Is the same thing. And you see that increase, but you see a saturation. Okay, it saturates at a certain point. The threshold. So when you've reached the stage of quote-unquote fully developed turbulence, then if you increase the scales, it doesn't the small scales, it doesn't seem to be changing the threshold very much. And I took this as a very strong indication that the dynamo will survive in a turbulent flow. It actually. So the question of whether the dynamo is being run by the mean flow, or is it the turbulent fluctuation that driving the dynamo? In a way to study this, with Yannick Ponty, we've studied the kinematic action from the mean flow as compared to the dynamic evolution in the DNS. Okay? So you're comparing the dynamo that you get from DNS, the full problem. On the other hand, you average the flow in time, and you throw this into a kinematic simulation. Now the kinematic simulation says there's two windows of dynamo action, and it's very easy to understand if you look at the pictures. One of them is what's happening between the cells of Taylor Green flow, strong shearing, and the second one is what is happening within the cell of one Taylor Green flow, which is, so this one is a VKS Dudley James type of dynamo, and this one just exists because in a 3D periodic simulation you're periodically shearing the flow. So this one is from the numerics. It's the other one that counts. And if you look at how the real threshold in critical magnetic Reynolds number varies with hydrodynamic Reynolds number, you see the real one increasing and saturating, and you see that those are the windows of mean flow action here for the low field mode and the high mode. Okay, so and you trying to decide whether the turbulence helps is you trying to decide whether these points are really lower than the diamonds. Okay, and you don't really get an answer. It's hard to know whether the full DNS problem is due to the structure of the flow or just its fluctuations. It's not subcriticality. Well, there isn't. I don't want to say much about it. All right. How much do I have to? I'll have
25 minutes.
Huh?
25
minutes.
plus.
Good. So I'm going to break this here for induction, turbulence, and all this, and now go to self-generation. So, you have any questions about that? It's a good time to ask them, otherwise I'll go to a self-generation process. Well, let's go. The first one that I'd like to describe before the VKS dynamo is a stupid Bullard dynamo that turns out to be a very useful toy in the lab. I'm assuming everyone's familiar with the Bullard dynamo, right?
No.
Yes?
No.
What do you mean, no?
We haven't had it in the school yet.
I thought it was Dynamo 101. Okay. So the Bullard dynamo is the disk dynamo. So what you do is, so you need to be able to draw. All right. You're rotating a disk. Okay. The disk rotates like this, and you suppose that there's a magnetic field like this. Okay. Now, induction is V cross B, so if V rotates like this and B rotates like this, you produce a current that, whichever way you want to do. Well, potential difference between precisely this point and the shaft. All right? That potential difference here, I could use to put electric light, and it will work, right? I crank that thing, and that works. Now, instead of putting a stupid light, what I can do is do a winding of that magnetic field, of that electric circuit in such a way that it produces that magnetic field. So I have to do it like this. Okay? So the current is going down this way, right across. A circuit like this will produce a magnetic field like this. So I don't need this anymore. All I need to do is rotate that. Okay? So the Bullard. So that's the Bullard dynamo.
Well, that's any initial current. And that an initial field. Just simple rotation generates.
Yeah. Well, and it's instability, right? If you have an initial field, then you produce an initial potential difference, which produces a field, which produces a potential difference, and there you go. Right? Chris, is that 1955? From memory? And if you look at it, the equation will be L di dt plus Ri is m omega I, m being the mutual induction between the two, omega the velocity of rotation. So when this is larger than that, you get dynamo action. That example is worth looking. If you haven't done it and you're interested in dynamo, that example is worth looking through and through. It has all the right ingredients. There isn't any more you can get directly more complicated with the equations. But on the physics, there isn't so much more that at least one may learn. One of them is that if I is a solution, minus I is a solution. Okay? So that if you, and you can play it, of course, if I started with a field like this, I would have a current in that direction. If I have a current in that direction, I have a field in that direction. That still works. Okay? So B and minus B are both solutions. And that's what you get from the equation. Second thing, you need induction to be larger than dissipation. And that's what you get from the equation. Third thing is that geometry matters. If you do the winding in the opposite direction, you have a critically non-working dynamo. If you do the winding, whenever you start a magnetic field like this, you apply one which is reversed. Okay, so you get no growth. So helicity and all these things are back. The symmetries are all there. What else? One question with which you can kill one first-year student is what happened to Lentz's law, saying that causes have to oppose, blah blah blah. All right? Well, that's not in this equation. It's the equation that says it's the mechanical equation that says T d omega dt, which is how that thing moves, is the usual driving torque, but in that case it's minus m omega I squared. And the torque is always braking torque, whether you're starting a dynamo or not starting a dynamo. It just depends that you have currents in there. And then you can, so that's the elementary example. You can push that elementary example into a slightly more complicated one if you, instead of operating the Billard dynamo at a constant velocity, you operate the Billard dynamo at a constant torque. And if you operate it at a constant torque, you start seeing oscillations. Okay? Because what happens is the torque will buy you some velocity, but the velocity is by reducing the torque, so the thing is slowing down, it is slowing down, the magnetic field goes down, if the magnetic field goes down, the braking torque goes down as well, and the thing speeds up. Okay? And you got oscillations, you got all kinds of, it's a fantastic example. So, unfortunately you can't do it. I spent a fair amount of time thinking about making one in the lab, just not to prove that Billard is right, of course he is, but just to play with the thing. So we finally succeeded in making one in the lab by cheating. All right? So how do you cheat in the lab? Somewhere in this coil you make a perfect current amplifier. So you generate a current I, which is G, the gain, times the potential difference, dAB here. And if G is perfectly linear, and that's all, and the amplifier is perfectly linear, it works like a Billard dynamo. So we've done one, which we're using to show kids at science fairs and all this. Last time I showed it, I was asking a kid if he knew what a compass is. He told me, my dad has a GPS.
So what, you demonstrate electric shock to the kids or what?
Well, that's, you try your best, and that takes like months to do. You're being shut down by a 6-year-old.
You could realize it without this amplifier in the laboratory if you do it sufficiently large. So it is 10 meters or so. We estimated it. There's a paper by Matthias Reinhardt. Okay, nobody else is constructed.
I know that paper. I really spent a lot of time trying to do this one. The problem is you speed so fast that you're trying to have balance problems and material resistance issues. It's a very hard. It's maybe it's feasible.
Sufficiently large dimensions you can read. Okay, that's not important.
Superconductors would be nice too. Well, you could. I mean, all you have to do is beat the resistance, huh? But it's a tremendous example. Okay, that really is one that is worth looking at. So here is another way to cheat, which I call the Billard from Common dynamo. So you have the fluid and the propellers. I was showing to you that when you counter-rotate onto an initially uniform magnetic field along the axis, you distort it in that way. Okay? Therefore, generating the some amount of toroidal field. Okay? Now, the field you started with is being applied by coils. Okay? those field lines create a B theta. Okay, so what you do is you put the magnetometer here, you measure the value of B theta, and you use that to create the current that goes into the coil. Okay? Linear amplifier. The whole trick is linear amplifier. Is one thing that makes the thing so hard, because any bias has you. So, just one point about this one. Cheating on the Bullard dynamo is very easy. You start rotating, you put in a simple amplifier, it will create a magnetic field. What you have to show that it is not the bias of the amplifier that creates the magnetic field. You have to show that it reverses, and it does. You have to show that it has the same probability of going in any direction. Okay, it's the thing that makes the amplifier complicated. So here you can put that linear amplifier here, and you use that to drive the coils. Okay? In which case you are, so you have an alpha omega dynamo in which omega is in the fluid and alpha is the amplifier. Okay? The good thing is that there's a number of things you control here. You have an alpha omega with controllable alpha coefficients and a turbulent fluid on top of it. So it's not exactly a dynamo, but it has many interesting features. And the idea came when we realized that that portion of field lines is associated with a potential difference along the axis, therefore being able to drive the current. So that's how it works, and of course it makes a dynamo, right? You've done everything for it. You can. How do I lower this?
You go inside. It says.
The threshold is for you to choose. Okay. The threshold is nothing else than the gain of the amplifier. Okay. So the threshold is for you to choose, and it does. It bifurcates to a dynamo. That dynamo has both polarities. Of course, B and minus B are solution, and there's two features. First, it reverses spontaneously. Okay. And the second thing is that it proceeds to a dynamo bifurcation via something that people call the on-off scenario, which is when you're near the threshold or in that vicinity here, what happens is sometimes you have fluctuations where the omega is strong enough so that the alpha you've prescribed times omega is larger than 1, the critical threshold, and you have a dynamo burst. Many times the fluctuations are not strong enough, and then you don't have that. So you proceed to dynamo via these bursts. And the very interesting thing here is the turbulent fluctuations that drive the whole thing. So you have only half of the process, but you know what turbulence does on the large scale on the dynamo mechanism. And, well, I don't know how versed people are in on-off dynamo, but you're slowly going from a state where the most probable, that's a probability distribution of the magnetic field, the most probable event is at B equals 0 to the most probable event being as B equal to B saturation. Now, there's two regimes you can use, and of these two we've only used one at the moment. One is that the max value of the field you grow is just limited by the power supply. Okay, you get into a stage where you get some toroidal field which you amplify in the loops, and when you hit the max current that your amplifier can produce, that's it. And here, this is what gives this value here. And at that max value, the interaction parameter is small. That is, the flow is not changed. What we're doing now is having that max value enough to modify the flow. therefore have a controlled way into which the flow is. So the saturation here is artificial as opposed to in a real dynamo where the velocity field is changed. And what we hope with this setup is to be able to change the level of the saturation with increasing currents so that you progressively increase the interaction parameter and see what you do on the flow. The other thing here is that it's a dynamo effect that is driven by the fluctuations, okay? And in a vessel like this, you can change the fluctuations by inserting all sorts of things into the vessel that will change the fluctuations. One of them is if you put a ring inside in the mid plane, if you put a ring here in the mid plane, what you do hydrodynamically is you pin the shear layer. Instead of that shear layer oscillating like mad, you've pinned it to one position. Once you've pinned it to one position here, you've reduced tremendously the fluctuation in that. And when you reduce the fluctuations that you have as opposed to a case when it is free, you see that the dynamics of the dynamo, which is reversing erratically when there is no ring here, remains to an almost constant and change level when you put a ring. That is, in these type of scenarios, the growth of the dynamo and its stability is strongly attached to the stability and the fluctuations of the large scales. Alright? And it's what we've been studying. I think I'm going to break here, Axel, and answer questions, because then I'm going to go into VKS generation on. I think that's a good point.
So let's ask for some questions.
To start.
So, questions, please.
Not a question, but a comment. What you said about the palm dynamo may generate the impression that it is a turbulent alpha effect dynamo. It is not the case.
It is not the case. I'm sorry. Yes.
That it is a modified Ponomarenko dynamo working with a regular flow.
Absolutely.
But in practice, you have a superimposed turbulence.
Yes.
And we, Adrian Stepanov and I, asked what is the effect of this turbulence? Can it have an alpha effect which supports the original dynamo or counteracts it?
Oh.
And in how to say, in the series approximation, you have no alpha effect, as long as the turbulence is homogeneous in the direction of the
torus.
azimuthal coordinate. And you have, if they have an inhomogeneity, then you may have an alpha effect which has been measured in the gallium experiment.
Yes, you're perfectly right. I'm sorry if that wasn't clear enough. I think I said that Perm was a periodic ring experiment. It is a Ponomarenko. I totally agree with you, and I do hope that they so the current status is that they're filling a larger torus now with sodium, hoping in a titanium vessel, hoping to run through.
You said that the beta effect was very small, sort of less than 2%.
Yeah.
Is that what you'd expect? I mean, what do you get if you just make? I mean, obviously the electrical conductivity of the fluid is quite large. So, but what do you get for the 1/3 d squared? I mean, what is that?
It's the point that I was trying to make is I don't know any way out of what I know of that turbulence flow to make this of the order of what I measured.
Why? Because you have to make tau too small or something.
Because this is one.
Right. 1 meter per second squared.
Yeah.
Yeah.
This is one again. So you're going to make this 10 to the minus 3, 2.
Right. Yeah. And beta is.
And
2 or something.
Right. So I don't. Either if I take a short correlation time, you're going to decrease tau very much, but then it falls outside of the scopes of the parameters I have at hand. So I cannot use 1 over omega, the rotation of the disks. Certainly, the smallest Kolmogorov dissipation is way too small.
There's a bit of a problem.
Yeah, there's a bit of a problem. It's what I was pointing out. I guess that was my comment here is you really have to do what Karl-Heinz and Roger did. Those estimates are just too crude for most of flows that you will have with the shear, with the rotation, with all this. And I guess you've seen these in numerical experiments as well. You really need to go onto the details of what are all the contributions. The order of magnitude on the previous slide don't do this.
Jean-François, on the previous slide. So B is proportional to lambda minus 1, right? Lambda is electrical conductivity or resistivity, right?
Yeah.
It's large, beta is small. Together with alpha. Both are small if lambda is large.
So I should have phrased it differently. If I use what I get is orders of magnitude smaller than what I estimate using
in comparison
this
with this, right?
Yes. You use this from what I know of these flows. You do the back of the envelope thing, and you're 2 to 3 orders of magnitude away from what you measure.
Okay.
But then again, there's a contradiction. Again, I want to make this point that there's a contradiction only if you look at it from that point of view. If you look at it from this point of view and you try to see what are the strengths of these different terms, there's nothing that tells you they have all to be all over 1 that I know of. Yeah.
So do you actually know the coefficients in this formula?
Sorry?
Do you actually know the coefficients in this expression? And how do they compare with the?
Well, they compare favorably. I mean,
Yes.
in the case we've tried, or we have the signal, the one thing that has the right polarity is that term here. And if you do all the math that is in Karl-Heinz and Organ's paper, you turn out to with this estimate, which turns to be correct. Okay. Again, it's the point that it's the transport coefficient.
Yeah, so if you come back to the turbulent diffusivity, then what is the corresponding part in that big expression here for turbulent diffusion? The big expression for the Helm experiment.
Oh, I'm going to have. No, wait a minute. Where was that? No, I'm going the opposite direction. Sorry.
Yes, exactly.
Karl-Heinz, you need a guide. I'm not a guide.
This line would be the relevant one, and of course here.
Oh, what is connected with the curl of B?
Yes.
The beta 0 and beta D term.
Yes.
And also it corresponds to the omega plus J effect. The next line.
And are you saying that those coefficients too are in agreement favorably?
This in that particular case for the beta effect, I don't know of a detailed comparison of what the numerics does.
Okay. I mean, it's of course this expression, this beta here rather, which should be one wonders is it comparable with this, and if not, why exactly? I still would like to know that. And it could be because of the rotational influence. Rotation is rapid, for example, that quenches such parameters and other things. Okay.
Of course, this is the expression of 1 over 3 U squared. Tau is in the high conductivity limit. In the experiment, you are closer to the low conductivity limit, where it must be some modified.
Yes.
Sure. Exactly. Yeah. Okay. If there are no further questions, then let's.
But Axel, the conclusion is clear. These should be clarified. They should be sorted out. You have an experiment where indeed it should be turbulent, it should be understood.
This,
Why don't you discuss it tomorrow? Karl Heinz is here,
but
Axel is here, and you are here.
this, I think
Discuss it in the evening.
the
Solve it
major,
for tomorrow.
the major problem here is I think we're operating in different limits. The calculation and many assumptions that are hidden behind it assume that PM is of order 1, or possibly larger than 1. That is, everywhere, that's, if you make a sketch of the spectra, it's easier to understand. You have the velocity spectrum, and here we have the magnetic spectrum. Okay? Now, all the small scale of the velocity is basically acting when there is no magnetic energy. So all these ideas are not very true. Now, if the spectra are reversed, okay, at least the turbulent velocity field is acting on all scales where there is magnetic field. Okay? And you do expect those situations to be different. Okay? So at least from the theoretical point of view, I think we start to understand why this is so. Because all the small scale effects need no magnetic energy, basically. It's all being dissipated. Okay? Now, if you experimentally, if you want to settle and see how it works, you need to be operating experiments at Prandtl number equal to 1. Okay? As again, as I said yesterday, the only proposal I know is that Kerry Forrest of doing experiments in plasma. But this is not going to be soon. This is in progress.
Except that we have a large-scale dynamo simulation with helical turbulence and very small Prandtl number, 10 to the minus 3. And we find very much the expected behavior in that case. So
you're right.
So one case where the small Prandtl number case was not really causing a problem for the upper and either turbulent effects.
I don't think it is causing a problem. I think I'll show it tomorrow. But one's got to be careful about which estimates can be used in what context.
I think the small Prandtl number is not the problem. You should have a high enough magnetic Reynolds number. Even if you have a small Prandtl number but a high enough magnetic Reynolds number, is probably what you have in your simulation.
High enough for a small-scale dynamo action, you mean, right?
No, for any of the dynamo action. If you have both the small magnetic Reynolds number and the small Prandtl number, then you will have nothing like this.
No, we have a dynamo, of course, yeah. And we have small magnetic Prandtl number.
No, small magnetic Prandtl number, but what is your magnetic Reynolds number?
It's larger than 1 at least.
Yeah, and few tenths for it. In pair, it's few tenths, right?
Could we put numbers on this? So when you say small PM, small means?
10 to the minus 3.
And when you say RM is equal to 1?
In that case, it's 4, I think it is. Or 6.
And it's also a helical, right?
And by the way, these are, yes. So the critical one for dynamo action is about 1. So it's 4 times supercritical.
Yeah, because it's a helical dynamo where you put all the structures. It's like, it's a call-through experiment. Yeah. If you put it by hand, it works.
But in your experiment, the RM is also small, right?
No.
So in the gallium experiments that I've been showing you for the induction discussion alpha and beta, it was Rn was of the order 1 to 10, say, and PM was of the order of 10 to the minus 6 because it is gallium. Now the sodium experiments I'll describe tomorrow. Rm is of the order of
But there is
50.
there's no helicity kind of stuff.
It's
because one knows the fluctuation dynamo has a much larger critical Reynolds number. Whereas once you have helicity, it goes down.
right. But the thing that is puzzling me and that would need to be resolved at some point is that when you don't enforce helicity by some ways, at least experimentally, I don't know how it survives. That is, you could, if I imagine that if I replace the Karlsruhe experiment by an array of propellers that do these helical motions, I will never get a Karlsruhe flow. You put two propellers in a fluid and they don't do two nice columns. They immediately do instability, and what you have is a mess, as if you have the propellers in almost any directions. Okay? Because there is no such thing as that well-behaved helical cascade. And I said again, unless you rotate the whole thing, in which case you will stabilize those columns.
But I am sure that when I have such two propellers, the mean kinetic helicity of the flow is different from zero. The helicity, kinetic helicity, is an inviscid invariant of the of motion. Right?
Only if you really have zero viscosity.
Yes. But then this means that if you even have two propellers with the same sense of helicity, still you need to generate this helicity.
Oh yeah, you are.
Right? This is the helicity is generated due to the viscosity in the boundary layers of your propeller. Mm-hmm. And this can take time. So the fact that you have a flow driven by these propellers doesn't necessarily mean that the flow is helical.
Absolutely.
The total helicity can remain equal to zero. Can be equal to zero. Total helicity within your volume.
Absolutely, but the question is, how do you create, I mean, there's no many ways that I know how to create helicity in a flow. You know, you want helicity in a flow, you have some way experimentally, you have some way to tell it, do this. That's why this, we briefly discussed that yesterday, I think it's a very interesting perspective of the people in Dresden trying to do the precession experiment. That is, try to drive a dynamo from precessing flow. Because in that case, you have a volume forcing, which may eventually lead to helical structures on their own. Because otherwise, I don't know how to do helicity without imposing it from some way.
Can you measure the velocity field accurately enough? Say in a water experiment.
In a water experiment, this is getting near. In a water experiment, those high-speed tracking will presumably allow one to measure helicity in a laboratory flow within the next 3 to 5 years. It's an extremely...
This laser velocimetry, right?
Yeah, it's an extremely difficult thing. But I think people are going there. I know several groups, including us, trying to do this. But it's not there yet. And the second thing I don't understand is, if something is concerning the limit of nu equals 0, doesn't mean that it has to have a cascade when nu is non-zero, right?
Say it again? Sorry.
Well, people always do the helicity business by starting that if you put nu equal to 0, it's an invariant. Well, but when nu is non-zero, so what? What does it say is for nu equal not 0?
This probably means that evolution will be slow.
But if you drive something helically, I think the flow really becomes quickly helical. I don't think that was really a problem. That's what we see in simulations. What the magnetic field then does, of course, is another business.
No. Simulations are different, actually. Here, you have a propeller, right? It drives the flow because of what? Of pressure differences, right? But pressure force cannot make it helical. It only will become helical on average because of the viscosity in the boundary layers. This way helicity is generated. Because otherwise, for example, it will drive flow in this direction, but the back side of the propeller will also have some flow. It will produce, well, presumably, I think, the flow of opposite helicity, so that on total in the volume, On the short time scale, helicity will be 0. It will be positive in this side, negative on that side. And you need to wait for viscous time scale before it will build up.
I mean, you have rotating motion in one direction in which you propagate. That means helicity.
No. But as Jean-François was saying, but are you sure that there will be a return flow at a larger scale around the boundaries of your volume, which will be rotating the other way, so the plot helicity is 0? How can you be sure that it doesn't happen? In the code, in the computer, it's different. It's different. You just send particles in the right motion.
There's a very nice simulation that one can download from the web from Rudolf Friedrich in Münster. Okay, what he's done is put two vortices in 3D. Okay, extended. I mean the two vortices that you see normally in 2D. Put them in 3D. Okay, the columns, and let them run. Okay, well you put them exactly parallel, and what you see is the vortex pairing that you normally expect. Okay, and everything works out fine. And then is restart the simulation with the tiniest angle in between the two. All right, and the whole thing goes bazinga. And that's what I meant. I don't think I meant more than that, but that's exactly what I meant. I meant that vortices have that well-behaved helicity, blah blah blah, when they don't interact. But now, if you put them in a situation where all the dynamical instabilities will set in, you might get the result that Pablo Menini was showing recently, where you plot helicity as a function of scale. So you start with an ABC flow, you start with the Taylor-Green flow, and you look at how the helicity returns to isotropy in scale. And you see that both of them do it at the same rate. It's not because you start from fully helical that the interactions will prevent you from...
Wait a minute. Helicity and isotropy are not exclusive things. You have an isotropic helical flow, right? The fact that it becomes mass doesn't mean that it becomes non-helical. You can have a perfectly helical mass.
Yeah, sure. I mean, but this needs to be checked, and if one cannot really measure, we have to
I guess based on the math, you
hope that one can measure in the future, or I should do simulations in the meantime, of course, to hope that they converge.
But you know, but you should
certainly
simulate real propeller.
it is one, I think, for hydrodynamics, and that one has nothing to do with magnetic field. I think this one is a hydro challenge.
But then, Axel, you should simulate indeed a propeller. For example, in Bose, it's not just having a force in Navier-Stokes, no. You have indeed include boundary layers and all stuff
You
like
can
that.
do it, right?
Okay,
No, you can just
while
follow
we
a
are thinking
boundary.
about it, we should gradually migrate to the staircase, but I hope Anna will be there to take the photograph. I hope that all works out. I haven't double-checked that. So please converge towards the staircase then. And I believe it may be the lower one, further down, or something like that. It's better check.